Okay, here's a rational function. Notice, if this x squared were in the numerator, it'd be x to the minus 2, which would not make it a polynomial. That's why it's in the denominator. Rational functions. We're going to talk about graphing them. First of all, let's talk about the zeros. You know, where does this graph cross? If we were to graph this, where would it cross the x-axis? Your zeros all are determined by the numerator. This has nothing to do with 0. 0 down here is bad, and we'll get to that in a second. Okay, so let's factor the numerator and find out where our zeros are. What values of x make my numerator 0, and therefore the value of the function 0? They'll be our x-intercepts. Okay, so x squared plus 2x minus 8. I know when I do FOIL, I get x by x squared. X times x gets me my x squared. Since I have a negative here, I know I need a plus and a minus to get a negative number. So now I know anytime I have a negative, it's the difference of the factors of 8 that combine to get a plus 2. What are my factors of 8? I've got 1 and 8, 2 and 4. The difference of 2 and 4 is 2. Okay, the sign of my middle term is plus, so the bigger number goes there. Okay, so my zeros are going to be, what makes x minus 2 0? 2. So it'd be, right here would be a 0. Okay, and negative 4 plus 4 is 0, so I'd have another 0, 1, 2, 3, 4, negative 4. Okay, all right. Those values would get me 0. Okay? Now, let's look further. We've got to look at our denominator now and find out what makes 0 in the denominator. Remember, 0 in the denominator is a no-no. It makes the fraction undefined, or the function undefined. So let's continue to factor. This one's not too tough. The only 2 is a prime number. So 2x times x is really the only way to get 2x squared. Again, I've got a negative, so I know I'm dealing with plus and minus. And I want negative 3x. So 2 being a prime number, it's 1 times 2, right? If I put a 2 here, that would be positive 2x, and a 1 here would be a minus 2x. And that's not going to work out. That'll give us no middle term. So let's switch it around. Let's put our 2 here and a 1 here. Let's do our FOIL. 2x times x is 2x squared. My outer, negative 2 times 2x is negative 4x. And negative 4x plus this inner of plus x gets me my negative 3x. Okay? So outer, negative 4x. Inner, plus x, negative 3x. And 1 times negative 2 is negative 2. So we've got this factored. So right now, I look at what makes my denominator be, anything that makes either of these parentheses 0 is bad, because 0 times anything is 0, and we can't be this would make this undefined. 2 minus 2 is 0, so 2 x can't be 2. 2 is no longer in our domain. And right here, if x is negative 1/2, negative 1/2 times 2 makes that negative 1 plus 1 is 0. So negative 1/2 cannot equal x. So those two terms are no longer in our domain. Okay? All right? So that's our domain. Great. Now, let's look at x minus 2 over x minus 2. These two factors cancel out. Okay? So what that means is, I no longer need, I don't have to have a vertical asymptote at 2. Remember, we want to block off like a roadblock. This is where we get our vertical asymptotes, are strictly from the denominator. Vertical asymptotes, and I'll put one here at negative 1/2. Your calculator doesn't put these dashed lines. We just graph it that way. It's like a roadblock. It says, hey, we will not allow you to put in negative 1/2 as an input because it gives us a bad output. Okay, so you can't even put anything in here. Okay, graphs will approach this and bend away. Okay, So the denominator will dictate our domain. Okay, anything in the numerator, the domain could be anything, but once we have this denominator, now we can't have these values. Okay, so since this was not removable, we have a vertical asymptote. But here, this is what's called a removable discontinuity, and that's where sometimes you can't see it on the graphing calculator, but you will have a hole where the input 2 would be. There'd be like a hole, okay? If you can magnify the graph, but most graphs doesn't show up on your graphing calculator, okay? But if you plug in 2 here, this would be your graph's going to be something like this, but you should have your graphs. I'll show you in the graphing calculator. Anyway, so when you have a removable discontinuity, it's just going to be a hole in the graph like that, okay? But when it's not removable by being canceled out, it's a no-kidding asymptote at whatever that value is, and this value is negative 1/2, okay? All right, let's talk about, here's the graph right here, and you can see where this graph hits negative 1/2 and bends down, and this graph comes over. But notice where this horizontally hits an asymptote and levels off. How do we get our horizontal asymptotes? Okay, remember this acronym, Bow-Bow-Botten. Okay, this is about the exponents of the leading term. We don't care about the rest of this, just the leading terms. If it's bigger on the bottom, 0, y equals 0, the x-axis is your horizontal asymptote, okay? Like you would get for 1 over x, okay? That's x, there's not even an x here. X to the 0, x to the 1, bigger on bottom. You'll have the x-axis is your horizontal asymptote, okay? That means the graph seeks, as x gets very big or x gets very small, the graph, I kind of drew a terrible graph here, the y value of the graph will seek to that horizontal asymptote. As x gets very big, we approach 0, and as x gets very small, we approach 0, okay? Bigger on bottom, y equals 0, the x-axis. Bigger on top, none. There is no, if there's bigger on top, okay, if you're bigger on top, like x cubed over x squared, regardless of what comes after this, there's no horizontal asymptote, okay? It's not going to seek and level off at any value, all right? And finally, eats DC. Exponents are the same. Divide the coefficients. That's what we have here. I don't care about these terms. It's just the leading terms. These are going to be so much bigger. If you plug in 20 billion and this 20 billion, there's a huge difference between that extra 20 billion and then to the second power and first power. So these aren't relevant. It's just the leading terms. Exponents are the same, divide the coefficients. Well, this essentially is 1. So our horizontal asymptote will be y equals 1/2. Okay? And as you can see on this graph, this, as x gets very big, this is gradually going down, it's seeking 1/2, and as x gets very small, it's seeking 1/2. Okay, and you'd have to scroll out and really widen the window to see that, but that's what's going to happen in this graph. Your y values, your horizontal asymptotes are all about what y approaches. Okay? What y approaches is x gets very big or x approaches negative infinity, very small. Okay? What y approaches. Okay? What's your graph going to hit on a y value? Okay? All right? Numerator. Okay? That's it. Find my zeros. That's where we determine where what makes the function 0. Denominator. We find out what our domain can't be. What makes this undefined by having 0 in the denominator? And that will dictate vertical asymptotes, or if you can factor it out, it can be what's called a removable discontinuity, and you'll have, like in this case, a graph with maybe a hole at 2 where there is no 2, it's not in our domain, but there's just a hole there, not an asymptote, okay? All right, we'll talk more tomorrow. 10 minutes, that's good to go, okay? Have a good night.